Good afternoon, ladies and gentlemen. Am I audible at the back? The mic is working, I presume? Fine, thank you. It's just gone 3:30, sorry. 15:30, and so I'll begin on time. And the subject of the second lecture is what you see at the base of the map there. I'm going to talk about the broader tectonic framework of earthquake activity in Africa, but because it's the movement of plates and the frictional interactions between quakes that result in earthquakes, I'm going to go into a little bit of the history of plate tectonics from an African perspective over the last 50 years. And the reason why it's appropriate, the map that you see, that one was published exactly 50 years ago, and it's the first definition of the African plate. And I'll show it again later on. So that's important. Okay, let me get on. So these are the topics, 4 general areas of discussion, or what I'm going to be presenting this afternoon. They're each color-coded there, and you may have noticed yesterday that the title line on each slide corresponds to a color, where you see a color change, say from yellow to green, or from green to blue. That indicates that I've shifted to the next topic in this list over here. So we begin with this African perspective on plate tectonics at 50. But again, and because I had a question a little while ago, just to remind you, these are the plates. I do have a pointer that works and will hopefully stay working. And it's because the crust slides on this hotter, what we call the asthenosphere below. The driving forces that cause this movement, it used to be thought that they are kind of convection currents directly associated with the way different plates move, but that in fact we now know is not the case. There is not necessarily a deep convection system below mid-ocean ridges, for example. What is the case there is that mid-ocean ridges stand considerably above, about depth of about 2,500 meters on average, whereas the main ocean basins are about between 4,000 and 5,000 meters on average. And that gives rise to what we call a ridge push force. It's a gravitational push force that's pushing the continents or the plates apart in those regions. And the other thing is, as this oceanic crust cools, it becomes more dense than the mantle below. And therefore, when you have this situation where it begins to subduct, as we call it, there's a substantial force, probably the biggest dynamic force in the whole force balance, is what we call slab pull. And you can do a little experiment along these lines by wetting a towel and putting a towel on a bath, and then just pushing down the one end. You will notice that the towel will slide sideways. It's being dragged down by the part that goes underwater first. So that's largely what happens to plates, and that whole system can be decoupled from the actual broader patterns of mantle convection in the plastic asthenosphere and the deeper mantle. So those are just some, again, just to go over that. But looking over plate tectonics at 50, I found this quotation in a book by Peter Watson. It's called Terrible Beauty, The People and Ideas That Shaped the Modern Mind. And it's a history of scientific thought in a way. Because the modern mind is largely shaped by science. You can read the quote here, but he talks about the discoveries of earth science having arrived piecemeal, but they provided what he calls a romantically consistent story. One story, one narrative culminating in mankind. And he describes it as perhaps the crowning achievement of 20th century thought. And so that's a plug for what we these days call earth system science, and it's important. So the person that is really responsible for this is this person here, the author of this paper. Title is Rises, Trenches, Great Faults and Crustal Blocks, and that's his key figure in that paper. And this is the first definition of the extent of major tectonic plates on the Earth's surface. So this is Jason Morgan, and he's generally credited. There are a few people who are credited with many of the main ideas that arise out of plate tectonics, particularly one person by the name of Tuzo Wilson coined the concept of these big transform faults that relay displacement on one part of a spreading ridge to another. And you'll notice that the first line in Jason Morgan's abstract is that the transform fault concept is extended to a spherical surface. So that was his basic idea. He took it from a two-dimensional concept and put it into a global spherical context. And his paper was published in 1968, but he presented the idea in 1967. The paper that was published on the same concept and mainly dealing with the Northeast Pacific was by Dan Mackenzie. I'll show you a picture of Dan later on. So in the UK, for example, 1967 is taken as the 50th, 2017 is taken as the 50th anniversary year because of Dan's publication priority. But Jason actually preceded him, and they both acknowledge that sequence now. The other person that actually really took tectonics off a flat surface and worked on the sphere and wrote the first computer programs to play around, move, shift continents on a spherical surface and fit them together again in a quantitative way was this person over here. It's Alan Smith from Cambridge. And in this instance, this is his 1970 publication, again focusing on Africa and putting it at the center of a reconstruction, a quantitative reconstruction of Gondwanaland. I've interacted a lot. Unfortunately, Alan Smith passed away from cancer in August last year. We were due to meet at an October meeting in honor of Dan Mackenzie, but he unfortunately died before that. And improving on the Gondwanaland fit, particularly in the area of Mozambique, East Antarctica, and down here in the Antarctic area, is a lot of what I realized a long time ago that I could write the software to do spherical plate tectonics, and that's what I did way back in the late 70s. And so this is one of the things, pushing continents around was one of the things I started to do, largely inspired by Alan and Jason Morgan. What we're going to talk in terms of African tectonics, the first person to really talk about the Nubia and Somalia plates on either side of the East African Rift in North Africa is Dan Mackenzie, whose 1967 paper kicked off the plate tectonics concept in quite a big way. And Dan was the first person to actually provide what we call a reconstruction pole, that because as these continents, they're part of a spherical surface, so they caps on a spherical, on a globe, they rotate about a pole. If you move one with respect to another, it's actually rotating about what we call an Euler pole relative to the one you choose to keep fixed. And so Dan was the first to propose an Euler pole for Nubia and Somalia, somewhere in Central Africa. And the other important thing that he did in this paper was, because most of the work had been done on early plate tectonics off mid-ocean ridges, there you've got transform faults to give you direction, and you've got magnetic anomalies to give you rates of spreading. You don't have that in a continental rift. But what you do have is earthquakes, and if you can solve for the mechanism of the earthquakes, you can obtain what we call an earthquake slip vector. If it's moving horizontally, the slip vector will be parallel to the fault. If the one side slips down with respect to the other, the slip vector will be in the plane normal to the strike of the fault. So Dan was among the first to use what we call now just acronym ESVs, earthquake slip vectors, to then try and use those vectors wherever they are on the globe to estimate where the rotation pole is. They will lie along small circles around the rotation pole. And that was his key idea in terms of African tectonics, defining those two plates and doing that. The next important step with regard to global plate tectonics was what we call NUVAL 1. NU is an acronym for Northwestern University, which is in Evanston, suburb north of Chicago. And this is the lead author, Chuck DeMetz. The paper is DeMetz, Gordon, Argus, and Stein. Richard Gordon was the leader of the group, also Seth Stein. You can see over here that in 1990, that is well over 20 years after Dan McKenzie wrote his paper, Africa is still regarded as one plate. And I'll speak a little bit about this tomorrow, but I first met Chuck DeMetz in 1985. He was a PhD student. He gave his first talk at a big international conference at the AGU in San Francisco. And I happened to be on sabbatical leave in North America at the time, and I was in in the hall where he gave that talk. And he had this rather awkward African asking him about his position of the polar rotation between Nubia and Somalia. So we met then, and we've had lots of interaction over the years. And this is the source of one big frustration of his was not being able to use what we then called the Shadowsky slip ESVs, the slip vectors that had been compiled by a Princeton student by the name of Gordon Shadowsky. And Chuck and I worked on this for a while, but we couldn't get a stable solution. And so NUVAL 1 came out without the East African rift being recognized as a plate boundary. I published shortly afterwards, there was an earthquake in 1986 in the Lesotho-Natal border area, and this is out of a paper that I wrote partly in response to that. But it was using the earthquakes, which you see all of these little black circles along the mid-ocean ridges, Red Sea, the rift in the Carlsberg Ridge and so on. And then you can see the earthquakes as they appear down the East African Rift. You can also see a bunch of earthquakes in South Africa over here. Most of those are mining induced. They are not natural tectonic earthquakes. But here in this particular example, I showed the Nubia plate, I showed Somalia with different hash directions, and I showed by crossing the directions of the hasher over here, what I called in that paper an ambiguous region. And the reason why I did that was because I had, a few years previously, spent about a month on a ship called the RV Melville, where we were geophysically mapping and dredging the ridge between what we call the Detroit fracture zone over here and the fracture zones up here to south of Madagascar. And there it was quite apparent that we had some kind of important boundary over here in that region. It was also evident when we tracked across this part that there was something odd going on around the rift, what we call the Southwest Indian Ridge in that region. So I published that paper then. I've been corresponding with both Seth Stein and Richard Gordon, and that's them there. That's Richard Gordon, Seth over there. And they, about shortly afterwards, published this paper in which they first recognized the difference between a Nubia plate and a Somalia plate. and what they called a wide plate boundary zone. And you can see they have distinguished other wide plate boundary zones, either in the ocean, mainly in the ocean, in various regions, also in parts of North America, and of course in Eurasia. But this was a big wide plate boundary zone that they then spoke about. And this, what was important about this paper was that they had begun to use what we call space geodesy. Essentially, in those days, the GPS, the military satellites, American military satellite system, as it then largely was, the GPS, Global Positioning System, which was mainly intended to guide cruise missiles. This is quite an important juncture in plate tectonics, the adaptation of military GPS technology to the solution of or studying global plate motions. And Richard Gordon and Seth Stein were quite advanced there. We were together at a meeting in Washington and quite serendipitously in October 1992, because I happened to be passing through America on my way to another conference at the time, and I had a kind of week to spare. I was on some kind of 10-day economy ticket, and I, having friends at Princeton, I decided to spend the initial week in Princeton renewing contacts there. And I happened to run into Jason Morgan the day before this conference was due to start, and he said, "Oh, what are you doing? Why are you here?" I said, "Oh, well, I'm twiddling my thumbs for about a week before I go on to California." So he said, "Oh, I'm going down to this conference in Washington. Why don't you come with me?" I said, "But I'm not an investigator. I don't have an invitation." He said, "Don't worry about that. If anyone asks you, just tell them you're with me." And so I got dragged along to that, in which was really, apart from an earlier lecture of Jason's, was my introduction to space geodesy and using the GPS system with regard, also using other systems. We use the radio telescopes. And so after the DOSE meeting, I became involved with the astronomer in Cape Town, Bob Stobie, and the Hardebeespoort Radio Astronomical Observatory, in beginning to use the radio telescopes as well, what we call very long baseline interferometry. And we got, and also there's something called satellite laser ranging, where you have satellites which are effectively just reflective globes, and you can laser range to them, and that's another technique of tracking positions and motions on the Earth's surface. So these three techniques, along with others, were starting to become quite important, and those two people are quite important. I then, sometime later, published this paper because I was unhappy with the designation of the whole of this region as a so-called wide plate boundary zone, because I was persuaded that there were stable blocks surrounded by seismic belts. And so I published this paper in 2002. It was in the South Africa, and it was related to earthquake hazard. I was arguing that along the rifts and in other places there was substantially larger earthquake hazard than, say, in the middle of the Kalahari, for example, and there was also a stable block down in this part of the Southwest Indian Ocean, which was surrounded by more seismically active belts. The one thing I'll just again point out here, you can see I defined a UN plate there. UN there was an acronym for Ukerewe Nyanza, Lake Ukerewe, which is the indigenous name for Victoria. Subsequently, there was a Russian scientist Victor Kazman, who'd earlier defined a Victoria plate, and therefore, again, publication priority has dictated that my name for that plate was not accepted. But so we've gone on in African plate tectonics to now largely use the GPS and earthquake slip vectors to understand how the plates are moving, how fast, and in what directions. And this is the title of a paper that I wrote. Or I was a co-author with Eric Calais. He was the lead author. Eric was a professor at Purdue University in the United States. He's a Frenchman. He's now a professor at ENS, École Normale Supérieure in Paris. And he and I continue to collaborate in these areas. So we then were able to begin to define poles of rotation like these two star symbols over here, with also with the error ellipses, and that was the other important thing. We'd begun to quantify this and develop some kind of statistical index of how reliable our solutions were. And you can see that early on our solutions were, this was the 95% confidence circle, so that there was a fair amount of uncertainty about these things. But what a pole of rotation enables you to do is forecast directions and velocities along the boundary. And so the arrows over here are the model forecasts of rates and direction. There's a model, and that the length is equivalent to 5 millimeters a year. So you can see up in the north it's about 5 millimeters a year, coming down in the south much less, along the main Nubia-Somalia boundary. So those were the important features at that time. Subsequently, we've got, and this is Sarah Stamps. She was the lead author on this article. And Sarah was a PhD student of Eric's. She's now a professor at Virginia Tech in the US. And here you can see this is our Somalia-Nubia pole, much tighter, 95% confidence ellipse, and the velocities that you can see. I've highlighted some of the numbers. So that's a Nubia-Somalia boundary, but there are these other plates which we have defined between that. The now called Victoria plate, and then the Rovuma plate. So the plates, these intervening plates, by the way, their names have one common theme. Victoria is named after a lake. Rovuma is named after a river. And Lwandle is named after the ocean. Lwandle is Xhosa for ocean or sea. So we have various poles of rotation for these different elements. The 1.5 millimeter per year actually refers to rates of motion about the Rovuma Nubia pole, rising to about 3.8 millimeters a year in the region between Lake Malawi and Lake Tanganyika. So these are very slow rates of motion, and that's been one of the difficult things about African plate tectonics, is that this is the slowest moving major plate boundary on the planet. And so solving its problems has been, it's taken a long time. That's one of the reasons why, in this case, 40 years or thereabouts after plate tectonics, the global plate boundary data system, that's it over there, defined along the mid-ocean ridges. So this is Chuck de Metz again, and it was what is called the Morval model. Morval is acronym for mid-ocean ridge velocity model. And you can see here they have, again, with the newer data on the Southwest Indian Ridge, recognized that there is indeed a Lwandle plate between Nubia and Somalia. But they don't, in this model, they don't show Victoria and Rovuma. That is because there is no oceanic data to constrain movements along those plate boundaries. There is only the the rift and the earthquake data. And this is a model based exclusively on mid-ocean ridge magnetic anomaly and transform fault directions. And this is last year, the most recent paper in which Chuck Demetz and Eric Kalev collaborated. Chuck and a Russian colleague have redone all of the magnetic anomaly work along the Southwest Indian Ridge, and again made quite sure that this is indeed an intervening plate along that system. And then Eric has combined with that all of the GPS data across Africa. These are the main stations used in the circle symbols. The GPS sites in these to estimate the Nubia, Somalia, Antarctica angular velocities and others in the system. So we now have a fairly confident picture of what the main plate boundaries in the system are, where they are, how fast they are moving, with one exception. Eric and I still disagree about the position of Nubia Lwandle, and as I indicated yesterday, I think there's earthquake evidence here, and in particular going back to the historical 1850 event, that the Nubia Lwandle boundary actually comes through parts of South Africa here, and before, so it lies west of this big transform fault structure, or fossil transform fault structure along the Mozambique Ridge. That's an extension over there. What they have drawn is an extension of what we call the Andrew Bain fracture zone, which is one of the longest transform faults on in the global system. So that's the net. So that's why it's taken us quite a long time to build up this picture of African plate tectonics, what's going on, and the earthquakes and the slip directions of the earthquakes have played quite an important role in developing that picture. So it's taken a long time. It required the co-evolution of all of these things. You needed the satellites and the computer technology, the development of the science of what we call space geodesy now, and its application in tectonics, and then its integration with the earthquake data. All of those features combine to give us what we have today. The important part, however, is that in a sense, and this is this concept of a composite plate actually comes out of some of Richard Gordon's papers, in that it, particularly in the south, there's still a very strong dynamic coupling between the plates. They're moving very slowly. The poles of rotation for that part of the system, the Nubia-Somalia pole, is within the zone of plate boundary, which means that the plates are coupled, which means that there can be a null point on the plate boundary and a spreading zone north of it and a compressional zone south. So what that means is that one can have very high crustal stress anomalies developed in places like that. Those can be among the most dangerous places on the planet. And so that is something interesting that we need to be looking at. So the other, just to as an epilogue to close off this thing, I also found this paragraph in Peter Watson's book. And he here refers to the evolution of mankind, largely within the East African, the Rift Valley of East Africa. And work on tectonic plates has shown that this valley was the edge of just such a plate, perhaps accounting for some unknown reason for why mankind should have emerged here. Now there's quite an eminent French he's a British seismologist based in France by the name of Jeff King. His father was a former director of the Ugandan Geological Survey, and Jeff has been very conspicuous, along with a British archaeologist by the name of Jeff Bailey, in propounding the idea that the reason why humans are the way we are, why we don't rely on smell so much as eyesight when we are hunting, and we are very effective ambush predators, that mankind, the early Australopithecines, were able to survive in a Rift Valley context because in that kind of context they had a strategic advantage over the big cat predators, which they would not have had on a savanna. And so that's, may well be a reason why there's humans co-evolved with the East African rift system as its sort of cradle. So we come back. This is again switching the topic now. The East African rift system and the earthquakes of what we would now regard as an interplate origin between Nubia and Somalia, Victoria, Nubia, Victoria, Somalia, Rovuma, Nubia, Rovuma, Somalia, and so on down the ridge show, and with still quite poorly defined relationships in this southern area. But the other thing that, and I did point this out yesterday, there are interplate earthquakes that cluster along the East African rift system. But if you look at a map like this, there are many intraplate earthquakes well away from the East African rift system, and therefore we still have to begin to understand what exactly is going on in these intraplate systems. Are they fragments of or attempts at rifting into, away from the, in other words, are they attempt at propagating other rifts from the current southern part of the East African rift system or not? And the it so happened that early last year, 3rd of April, there was a magnitude 6.5 earthquake in an absolutely flat part of the Kalahari, this region of southeastern Botswana. This is the USGS isoseismal map. It was strongly felt in Johannesburg. This is Mustafa Magrahi provided me with a new digital version of the map in which he'd plotted the focal mechanism. So that's where it was. Johannesburg is down to the south of this particular little inset, just off to the south there. And what you also see on this is that Vunganai Midzi, who's with the Council for Geoscience in Pretoria, has had an array of seismographs deployed in this part of Botswana around the epicenter for some while. And they have been recording earthquakes around that over quite a surprisingly wide area. Very small earthquakes. We're talking getting down to magnitude 1. So there's still more to come out of this, and an interesting story developing, which, again, I'll probably have a little bit more to say about later on. So the question that this earthquake raised, and it came very shortly after this paper had been published. Again, Eric Calais, that's him there, and this is when he was visiting us at Amanus. That picture over there shows a GPS system on top of a borehole, because we not only, Eric and I have collaborated quite a bit on not only measuring horizontal motions of the plates, but we also measure vertical motions above aquifers, for example. We can have a 15 millimeter deformation of surface due to groundwater abstraction, and these are things that we are trying to detect. You can also have natural hydrological loading by reservoirs, or even heavy rainfall in mountains produces a crustal depression, and we can pick up those signals, and we are in some cases starting to use those kind of signals to interpret crustal properties from those. So So this paper came out proposing that these large earthquakes in stable continental plate interiors had a new paradigm was necessary. The story there is that with earthquakes along plate boundaries, and you go back to the Harry Fielding Reid's elastic rebound, so the plates are moving, the friction along the fault holds them together for a certain while up to the frictional strength of that fault. So elastic deformation is taking place. That whole zone around the fault is being loaded at a certain rate. But the key feature that Eric and Seth had noted, particularly in an area called New Madrid along the Mississippi River in the United States, is that there were very big magnitude 8 earthquakes in about 1811 in that area, about the same time as the Cape Town earthquakes. And it had been assumed that there was some kind of low rate of tectonic loading going on in that area. Eric and Seth had established a local network of GPS receivers over some years in that area, and they discovered that in fact there was zero tectonic loading in that. As far as they could measure over something like a decade, there was absolutely no load being imposed on that region. And so therefore, New Madrid and the ongoing seismicity was a mystery. Whereas, for example, the building regulations in the town of Memphis, or the city of Memphis, were being Californian, because of the magnitude 8 earthquakes in 1811, Californian-style building regulations were being imposed there. Seth began to argue that, no, this is nonsense. This is not California. This is not an area that's being actively tectonically loaded. If there was an earthquake in 1811, this place with zero tectonic loading is probably now extremely safe, because a 1 in 5,000 year earthquake, or even longer, has actually recently happened. It's not going to happen again anytime soon. And so there was that, he began to turn this around, and this has become, particularly in the US seismic hazard community, quite a controversial theme. So this paper was really about looking at the global intraplate earthquakes, the red dots. That's the original paper from the diagram from the paper. I have highlighted, for here is Toba series, which was put on as a Lisbon is there as well as an intraplate. I think from our discussion yesterday, I would argue that that is more a plate boundary event, but Agadir is there. But also what I've added on this diagram is last year's Botswana earthquake, because there's an argument now that we are wanting to maybe convene with 1969 Cape Forbelt earthquakes and the Botswana earthquake, organize some kind of symposium around this theme in Southern Africa, and that's a suggestion that came up between Eric, Mustafa Magrai, and myself early last year. So what I've been talking about is this difference. These are interplate earthquakes, and the idea is that fault strength is the main controlling factor, that tectonic loading builds up the stress until the point that the stress in the crust just exceeds the strength of the fault. And then the earthquake releases the stress, and then you start the cycle again. And that's the cycle of earthquakes along a typical, for example, San Andreas type fault. We know that there's not an exact recurrence period, but there's a statistical average. There's a 1 in 150 chance of a magnitude 7 earthquake. Whereas the intraplate paradigm that they are proposing is that there are 2 possible causes. One is that fault strength, as you can see, they've drawn fault strength as being a variable thing with geological time. So it's the fault strength that is changing, that there are things that are happening in the crust that change the strength of certain zones of ancient weakness. And when the stress in that region happens to, or the fault strength happens to hit the stress level in the crust at that time, then you have the earthquake, which drops everything to a much lower level of stress. The blue line is that you could have what they call transient stress perturbations. The stress is actually quite low, below fault strength, and then suddenly some kind of loading takes place. And that can be hydrological loading, either of natural type or artificial type, and that the stress suddenly goes up because of a transient, hits the fault strength, and then gets dropped again, and then resumes at a low level. That whole area has then, unlike the tectonic faults along the plate boundaries, that region is now comparatively safe. The stress has dropped below the fault strength, and it remains below fault strength. There's no, or maybe will climb very slowly because of very low rates of tectonic loading. So that's the argument, that this is the new paradigm, that things like 1809, 1969, Tilbach series, and the Botswana earthquake are these fairly unusual weak events. So when you look, this is another friend of mine, Andre Kiko from he's now University of Pretoria. This is his seismic hazard map of South Africa. And you can see these are typical bullseye hazard maps. You have a red sort of bullseye around Cape Town, 1809. You've got another red bullseye around Tilbach series, 1969. And these are regarded as being areas now in this concept of high seismic hazard. This is a 1950 sometime earthquake near Willamore. Not a very big one. So that is the earthquake hazard of the Western Cape according to traditional plate boundary style seismic hazard estimations. The question that is posed now in terms of the GPS studies is these possibly should be the green areas. All of these other parts over here should be actually red. And as I say, that is a rather controversial point of view. So that's the lessons of the Botswana earthquake. And as I say, this is a zoom in on the thing. That's its epicenter. You can see the yellow lines. These are the main isoseismals as plotted by the USGS Johannesburg down here. Intriguing thing there was that, and this is Max Wies's forecast. The earthquake occurred at 7:40 p.m. in the evening. I got this on my email just a little more than half an hour later. But I'd already been alerted to something unusual because my wife had called me in to she happened to be watching TV and a news reader at the time, and I got this vision of the somewhat panicked, wide-eyed reporter describing the shaking going on in the news studio. What was coincidental was that earlier that morning I'd been woken up by phone calls to ask about another earthquake, and that was the same day at about 5 a.m. in the morning, the Klerksdorp earthquake, which was a mining-induced event, magnitude 4.6, which nevertheless shook up considerable parts of the Johannesburg. So that was the it was the event 3rd of April last year, but it was in a region where we've had a number of big magnitude 5 earthquakes over the last, all of this is since 2000, the earthquakes that are labeled there. And it is particularly around here. That was the biggest one, magnitude 5.4 in 2014. This is the area where 2 of the world's deepest mines, quite new mines, are located. There's the Moab Kutsong mine around about here, and the Great Naligwa mine over there. And so this earthquake was almost certainly triggered by very deep mining, around about 3 kilometer level at Great Naligwa. That's that over there. That was the Orkney earthquake. I believe one person was killed by a collapsing wall there. And this is the 2014 event. One of the things that I noticed that there were things being recorded in southeastern Botswana, so it was not entirely aseismic. That's the area over there. So this was something I extracted in 2014. The mining-induced earthquakes, these are almost certainly man-made, but these things over here, there was some question about that. So this is the focal mechanism. It tells you that this is being stretched in a northeast to southwest direction. It's normal faulting. That was the active, one of these two planes of the active fault. The other thing that was intriguing about this at the time was that there was a new diamond mine called Gago mine, very shallow thing, and it wasn't actually active at this time. That's a zoom in on this little feature there. And so there was initially some speculation that this earthquake had something to do with either the mine there or coal seam gas work that's being done off in this region just to the north and east of Botswana. So we began to look at this. A colleague of mine, Richard Wonnacott, he shares an office with me in Muizenberg, and Richard had collaborated with Rocco Malsavisi from Florida in this paper. So this is where they were wanting to understand how rigid is a rigid crust. When we talk about plates being rigid, can we use the Trignet system in South Africa to quantify that? And they had published this in 2013, in which you can see they've got a strain rate recorded over here from 0.1 nanostrains to 10 nanostrains per year. 1 nanostrain per year, just let me give you an idea of that. If you have 1,000 kilometer distance, that's 1 billion millimeters. And changing that by 1 millimeter is 1 nanostrain. So if you change 1,000 kilometers by 1 millimeter a year, that's what you are measuring here. So we have parts of South Africa where we reckon there's less than 1 nanostrain per year going on. And there's a very rigid core between Kuruman, Springbok, Priska, Uppington there. There are some areas where one has slightly higher strains, but we immediately noticed after Botswana that back then this Mafeking Ellisras, or what is now Lephalale, was an anomaly. And also the Windhoek Mafeking line was showing an anomalous reading. And we went back to check on that. As a result of Botswana, we also looked at the stress patterns, because we could define the principal stress directions now. So that's the maximum horizontal compression. Maximum stress is vertical, and the least stress is at right angles to the lines. And so what you see over here, these are seismic belts that you can define. There is an area of anomalous seismic activity through over here. And that separates normal faulting, which are the red lines, from strike-slip faulting, which are the green lines down over here. So we have a crustal stress boundary along what we call the Senqu seismic belt. But you can see that from our measurements of strain rates, there is no actual tectonic loading across that. So these are anomalous intraplate earthquakes. And the only anomalous area that we were able to find was Richards Bay, which seems to be in the plate boundary zone, going up to about, I think this is up to 8 nanostrains per year in that area. So we've been doing this kind of thing, looking at the length changes between GPS stations in South Africa. This is and we excluded Mafeking as an anomaly. You can see over here that the length change, which is a shortening between Ellisras and Mafeking, is opposed by a lengthening between Kuruman and Mafeking. And Mafeking is showing all kinds of anomalous ups and downs, which indicates to us that there is some local, whatever it is, but there's monument instability. That is not a natural effect. It's an artifact of the construction of that continuously operating GPS site. If you map the Ellisras Kuruman length change, you get a very slow extension. What you also see is that there are seasonal fluctuations. That's partly this is in a horizontal plane, but it's a reflection of seasonal fluctuations related to hydrological loading. And we extended our work to Noto in Sicily, Maspalomas, St. Helena, and some of these other big African GPS, long-serving network parts of what is called the IGS network in South Africa, to show that Nubia is pretty much a very rigid plate. Something like the distance between Noto and Zamb is changing at less than 0.1 nanostrain per year. So, and on the other hand, as I say, we've got a southeasterly motion of Richards Bay at about 1 millimeter a year, which is consistent with the Lwanli-Nubia boundary forecast in that region. So the other thing that had been very shortly after this, and these are pictures that were appearing on Twitter actually. So Twitter has become a way of getting information out about earthquakes. This is what we call INSAR. INSAR is an acronym for Interferometric Synthetic Aperture Radar. And if you have radar satellites which pass more than twice over the same point on the Earth's surface in succession, you can actually measure centimeter to millimeter differences in the surface there. So you can see around the epicenter over here, there's that kind of pattern. That's what is observed. This is the model of something like 20 millimeters of deformation from an event of about 1.5 meters slip at a depth of about 25 kilometers in the crust. Very deep event. And so these this was coming out about 9 days after the event. Those results were already obtained because the satellite had gone over before April the 3rd, and there was a pass over, I think it was April the 7th. The same satellite went back over, and that was the difference between the first pass and the second pass. So, and then combining these sort of radar satellite with the aeromagnetic map, which had been obtained by the Botswana authorities, that had been around for a while. This is a student at Oklahoma State University. He was able to show that there was a pre-existing crustal structure there that earthquake, which is about there, coincided with. So his supervisor is Estella Otakwana. She's the second author on this paper, which was published late last year. Estella is a geophysicist originally from Cameroon. She was, at the time, until recently, she was head of the Boones Pickens School of Geology at Oklahoma State University. So she's now gone. She's one of these people from an SO country in the US. And she is now Dean of the College of Earth, Ocean and Environmental Studies at the University of Delaware. So I've known Estella since 1984. And it was largely through her that I got to Oklahoma to look at the fracking earthquake issue and all the wastewater disposal earthquake issue there, because there were certain things that another African could say that the head of Boone Pickens School of Geology. And Boone Pickens is a famous Oklahoma oil man that she couldn't say. So this is, again, going back to where that earthquake was and what it is on. Way back in 1985, we had already identified those structures running in that region there as a boundary between what we call the Magondi subprovince and an aqua block, which relates to a 2 billion year old collision between two different terrains forming the deep crust in that area. So that's, again, it's a zone of long-lived crustal weakness, and so there are lots of interesting stories that are still going to come out about that, we believe, in the future. And it again relates to this the stress province. So I'm changing theme again, just wrapping up now. There is something called the World Stress Map Project. If you want to know anything about it, that's the website. And these were way back in, this is a 2000 edition. This is a 1997 edition, which I was using for other purposes. But I put the Botswana result in, so that's the new result with its stress direction and type. It's, again, the reds correspond to normal faults. That's the definition of a normal fault. The greens over here correspond to strike slip faults. That's there. And so we have the distinction between what I call the Cape Stress Province and I called it the Transgarip across the Orange, or Transgarip River Province. And the question is, what are these stress provinces? What are they related to? And are they significant for seismic hazard in different parts of South Africa, whether it's the mining areas or the other areas? And so this is this is Peter Bird, is a retired professor from University of California, Los Angeles. He's produced what is called a finite element model of the lithosphere. It's a quasi 3D thing in which he's modeled on a global basis the stresses or the stress anomalies. Is something which he's defined as a vertical integrated stress anomaly. And if you look at stress anomalies along big plate boundaries, they are not that big or extensive. But within these wide plate boundary zones, and in particular very slow-moving plate boundary zones, is something called the India-Capricorn boundary over here, offshore of Sumatra. And that's got the complication of the Sumatra Trench there. That is the biggest stress anomaly on the planet. The second biggest stress anomaly on the planet is right here, offshore of South Africa. Whereas in that part of the Indian Ocean, we've had the biggest intraplate strike slip earthquake in recorded history. Well, that's only a century or so, magnitude 8.7 in April 2012. The question was, again, 1850, May 21st, was that likely there, and is it part of the same issue of very rare, very big earthquakes along very slow-moving, developing plate boundaries? The Capricorn India is a developing plate boundary. This is a developing plate boundary in oceanic crust. And therefore, the issue of stress in this part of Southern Africa and what goes on, for example, in the Karoo Basin, could be a quite important thing. So we're talking about very strong dynamic coupling affecting the boundaries there. It's got seismic tectonic implications of the whole of African kinematics, is about very ultra slow, less than 5 millimeter a year, extending boundaries. The question of what the probability of great events. There's been a tendency, because they haven't occurred in historical time, to say along rift zones like East Africa, magnitude 8 events have never occurred in recorded history and therefore can't ever occur. We don't think that's true. You can have magnitude 8 and have had magnitude 8 earthquakes along the East African rift system. Magnitude 8 earthquakes, like New Madrid in the eastern US, have occurred in a completely intraplate environment, and they could occur in Africa in the same way. So, and then using the modern technology to map the stress regimes and the strain rates and use those to estimate hazard and risk remains the objective of this kind of work. So again, I've run just about an hour there, a little bit longer than I intended to, but that's if anyone wants. Any questions, or I've left you all gobsmacked? Sure. Yeah, they've got to look at mainly from the point of view, not only earthquake hazard, but mainly from the point of view of submarine landslides and tsunami, local tsunami hazard. So that's been that has been one of the focuses of investigation at Taspen, for example. Yeah. Sorry, John? No, well, 50 years ago we didn't have GPS, and we didn't have the digital seismology that would give us the earthquake slip vectors so reasonably accurately. So, yeah, all of this African tectonics required modern computer technology, digital seismology, and GPS, and now, of course, also radar satellites. Yeah. Sure. Hi, Philip.
On one of the maps you showed the Witwatersrand, and I'm just almost curious why there's no activity there.
The Witwatersrand there are small earthquakes, and maybe I could go back to that. I'll put it up and refer to it later on. But the Witwatersrand is the trace of the Tristan da Cunha hotspot, or the plume, mantle plume. So it's a fossil volcanic construct, like the Hawaiian island ridges and so on, and that's what it is. So it's in an intraplate environment. There's been no actual tectonics there other than related to the volcanoes. The plate has been moving northeastwards relative to a fixed hotspot, and therefore the plume has the plume trace or trail has been left as a volcanic chain.